Hello and welcome to Ask Echometer. My name is Carrie Ann Taylor, and along with myself from Echometer today, we have the infamous Gustavo Fernandez presiding over the chat in our Q&A session. Also, Ken Skinner, Tony Podio, Dieter Becker, and Lynn Rowland, who will be presenting today. We want these sessions to be interactive. We'd like to see you and to hear from you. We welcome your questions and comments, and our goal is to answer all the questions during the session. We have opened up the chat to start accepting questions by text entry right away. If you don't see your chat window, click on that chat icon at the bottom of your screen. You'll see the chat window pop up. Send us a quick hello or tell us where you're from. You can type your questions or comments there and see the questions and comments from other participants as well. If we see a question that can be answered quickly, we'll answer it in the chat. If it's something that might benefit everyone to hear, then we'll answer that during our Q&A session. We have an Ask Echometer webpage that is accessible from our echometer.com website, and you can go there right now if you'd like and download the Session 22 PDF documentation bundle. You'll find a copy of today's presentation, a how-to document that steps through installing and acquiring power data, and 4 technical papers that will all be referenced today. Right next to that PDF bundle link is a link to download the TAM example file that Lynn is going to use today. If you don't already have the TAM 1.7 software installed on your computer, you can install it from the software page, or there's a link directly from the home page to that 1.7 install. So today's session is titled Motor Power Current Voltage Measurements and Analysis. So Lynn, I will turn it over to you now.
Thank you, Carrie Ann. We're going to talk about acquiring power, and the way we're going to organize this presentation is first I'm going to talk about a general presentation that we are discussing various points that are covered in these reference papers that are attached. These links are not links, but these papers that are listed here. And then we'll answer questions. I think Carrie and I said this. And then at the very end, we'll do a how-to on how to acquire power data. So if you're interested on how to connect the equipment and use the power probes to acquire data, then you'll probably want to wait till the last 30 minutes or so of this 2-hour presentation to see that. Now, we did an online seminar, Ask Echometer number 12, back in August of the 5th, 2020, where we talked about the different methods we can use to do net torque and gearbox balancing calculations. And that's what we talk about using the power probe. So I'll talk about that a little bit in this presentation, but if you're really interested, but the main reference will be this reference right here. We're going to talk about efficiency and other things that we can use power for primarily during this presentation. This is a picture of the power probes, the wired power probes connected into a panel. I took this picture back in 1993. And we realized back then that we needed to use this type of equipment if we wanted to find wells that had inefficient operations due to mechanical losses. And so the power was one of our primary operating costs, and you just can't look at a pump unit or an electric motor or look at the wellhead and see that it's not efficient. You have to be able to measure the input power and compare it to the power at the polish rod and the power required to lift the fluid to the surface. And the power probes are accurate. They're representative power, and they can be used for lots of analysis on the well that we'll talk about. When you go to a well and you collect amps and current, amps or current and kW and volts, then you can use that information to understand your efficiency of your overall efficiency of the pumping system. And when you compare the input power to the polished watt horsepower, then usually you have about 20% losses unless there is a problem at the well, a problem in the surface equipment. So you should expect to see around 80% efficiency of the surface equipment. If your motor's normally loaded, if it's not lightly loaded, we'll talk about all that during this presentation. When you look at the input power, usually about half of that power that you input to the system is used to lift the fluid to the surface. So we call the overall system efficiency of a suck-rod pumping unit that's properly maintained, the pump is full, it's usually going to be about half, 50%. When we measure the power, we can see how much power we're using per stroke. We can see the dollars it costs per month for us to use that power to produce a well. We can see the dollars per barrel of oil or water, and we can see the demand that the power company is going to maybe charge us for, because they have to provide a generation of capacity to provide the power that we need. And then we can also see the kW that we're inputting throughout the stroke. Now, the current flows back and forth through the motor under cyclic load. And so the load is cyclic because the motor has to help lift the rods on the upstroke and then help lift the weights on the downstroke. And so that's a cyclic load, and the current has peaks and valleys, and the changing flow of current can overcome the thermal rating of the motor and cause it to overheat and burn up. And so we can measure that current, and we can tell you if the motor is at risk of thermal overload. Now, most pumping units generate power during the stroke, and that's when the weights push the motor faster than its normal synchronous speed, and usually that's 1200 RPM. And so when you generate that power, the power goes back onto the power line. And a long time ago, I could actually see the meter would turn backwards, but now the power companies have become wise to that, and they don't let the meter go backwards, and usually we don't get a credit for that. In some cases, deregulation allows us to get a credit for the power we generate during a stroke. We see the gearbox, the kW and gearbox torque are directly proportional, and we can calculate if the gearbox is overloaded, and we'll talk about that. We can see where to move the weights to minimize the power required to lift the rods and the power required to lift the weights, and properly balance the loading on the gearbox. And that will make the motor have less cyclic loads and less heat lost to the current runs the motor. We can use the power probe, the power probe, to tell us where to place the counterweights on the crank to minimize our, in fact, reduce overload and to balance the pump unit. And then we'll talk about how you calculate the line losses from the transformer to the pumping unit based on the new wireless power probe. We can measure the volts also. Now, safety is important, and you need to be certified to open the power panel and connect the power probes, and you should always exercise safety and check the panel that it's not hot. Disconnect the power. Never put your hands inside the power panel. If there's something that looks bad inside, or if you think the power is not disconnected, or if you see a burnt area, you should call an electrician and get that repaired. Some companies don't allow their employees to open up the panel, and may even have to have an electrician open the panel. So Echometer has developed with the wireless power probes a fixed power adapter that you can place inside the panel and not have to open the panel to connect the power probes, which is a good thing. We'll talk about that. Now, this is a picture of the wired power probes, and this is Rusty connecting the power probe inside the panel. And we can measure the thermal current that causes heating. We can measure the current flow, the real current, and we can measure the kW even during a stroke. And we measure it at up to 60 samples per second. And we can use that to do all kinds of analysis of the well. And this shows us that we have these two little clamps here are called current transducers, and we typically connect them on the outside two wires of a three-phase power. And so this one says on the right wire, and the yellow part faces up where the transformer is this way. And then this one says on the left wire and it's facing up. You need to make sure that the cable goes through the clamp and it's about the same, about centered, and it's closed. The clamp needs to be closed. And these are the three, 1, 2, 3 voltage connectors, and you're going to want to connect it onto a bare metal so that you can get the right wire, the center wire, and the left wire connected. And we use the volts and the current to calculate the kW, and we output from the sensor, we output this wire sensor, the kW, and the amps. Now this is the wiring harness and the wireless power probe adapter that we use for the wireless system. And you can see here it has a longer alligator clips. These were the old clips we used to have, and we replaced those with longer. You don't have to get as close to the connections with the longer alligator clips, but these are labeled also center, right, and then left. And these are your two current sensors, and then this device outputs for the wireless system as you acquire dynamometer data, the amps and the kW and the volts. And so you get an extra signal, the voltage, that we're able to then use that we could use then to calculate the line losses. So we'll talk about this a little bit more and a lot more in the last half of the presentation. These are the fixed power adapters, and this is it's a little package that you buy that has a template and a cover for the sensor so it's watertight, and these two current transducers here that are used to read the amps, and then there's 1, 2, 3 wires for the volts, and then you just don't open the panel and plug your radio. This is your power probe radio, and this unscrews right here into this fixture, and then you're ready to go and acquire data. And so here we have the radio for the power probe plugged in to the fixed power adapter, and we have line of sight to the base station, and we can talk back and forth and acquire this data simultaneously as we acquire the dynamometer data when we're testing the well. Now this is a conventional pump unit, and we have our panel back here at the back, typically where we would attach the power probes. This is our electric motor that we're able to simulate the kW into from our power input to the system, and we're going to use that to analyze the net torque on the gearbox and some other parameters we'll talk about. When you look at the pumping unit from the side with your pumping unit, the polish rod would be in your right hand as you were facing the pumping unit from the side. This rotation is clockwise, and this rotation is counterclockwise, and that's one of the things that you should record if you're trying to do mechanical torque. The power probe, though, typically is just used from along with the dynamometer data. You're going to be able to use that data to determine where the weights need to be placed without knowing the geometry of the pumping unit. So it's a very simple, quick device, quick and easy to use, and you don't need to know the geometry of the pumping unit or where the weights are. But it's also very nice to know what weights and cranks on the pumping unit, because I like to compare the net torque from the gearbox mechanical calculation to the torque calculated from the power probes, and they typically should match. And then you can be more comfortable about where to move the weights based on the recommendation of using power plus recommendation in the mechanical API torque calculation based on the counterbalance moment and the dynamometer loads that you measured. So I prefer to do both when I can, and then I'm more comfortable if I can only use one of them on some wells that don't have either electric motor, or I don't know the weights and counterweights or something about the pumping unit. So it's nice to use both methods. Now this is a plot here of your net torque on your gearbox, but the red curve is from the mechanical method that's talked about in the previous presentation, I think session number 12, and then the black curve is output from the power probes. And we see that this is our pumping unit right here, and it's a conventional pumping unit. And let me get this thing going here. And this peak load represents this peak gearbox torque on the upstroke, and this minimum load here represents the peak torque, net torque on the gearbox on the downstroke. And you see the same shape and the same magnitude, both from the red line and the black line, both from the mechanical torque calculation methods and from the power net torque calculations, that this conventional unit has a peak on the left side on picking up the rods and a peak on the right side lifting up the weights, and it has two valleys. So there's two peaks and two valleys for a conventional pumping unit. And the motor, the electric motor power signature is the same as the net torque signature for this type of pumping unit. So this type of pumping unit is a conventional unit, and you can typically recognize a conventional unit because by looking at the power signature, because almost all of them have two peaks and two valleys. Now, when you look at a marked pumping unit, a marked pumping unit has a crank that's bent, and we call that a phase angle, and that's an attempt to get the torque from the counterbalance torque more in phase with rod loading, and it results in a smaller gearbox, a lower amount of torque. And so when you look at a mark unit, the net torque curve doesn't have two peaks and two valleys. It has usually two large peaks. This is the peak here picking up the rods. This is the peak here picking up the weights. But this peak right here in the middle is usually sharp, and it can be as high as these two peaks, but usually it's less. But it's due to the crank, the phase angle of the crank. And so mark units always have, I like to say, three peaks. And that's the signature of a mark pumping unit compared to conventional. And each type of pumping unit will have its own power signature and net torque signature that you can use to identify the type of pumping unit. Now, I marked right here on this, I put an arrow and marked where the zero torque occurs. And that's when the motor is no longer loaded because the torque on the gearbox is zero. And so that's when, at that point in time, the motor, when it goes faster than synchronous speed, which is typically 1200 RPM, you'll see that the motor here starts to output some negative kW, which means that the motor is converting either the rods falling or the weights falling from potential energy into power, into kinetic energy, and you could view that as a generation of green power. So one of the things I like to say is that when you look at the power plot of net torque on a pumping unit for a stroke, you're a green energy generator, and you believe in being environmentally friendly and generating power using green energy generation methods. This is for converting gravity into power. And so this is the example we'll look at later. We'll look at this example later when we finish the presentation. And I tried to go through, and for every example of data, I've tried to attach the link to we have like 8 different examples in the example file of TAM, different TAM example data we'll talk about. And also the pages, each slide's numbered, so you can reference back to a particular slide if you have a question. Now, when we talk about, this is an example of balance and imbalance of upstroke and downstroke. So when you look at these three graphs here, there's the upstroke and the downstroke, and for this one pump cycle, and then here's another upstroke and downstroke, and here's one upstroke and downstroke. And when we look at this signature, this shape, this would be for a conventional pump unit, and we would say that the upstroke net peak torque, or net kW, is much higher than the downstroke. And so we're spending a lot more energy trying to lift the rods than we are trying to lift the weights, and so we would classify this signature as rod heavy. And we look at this signature of either torque or power, they look the same. We would see that this peak on the downstroke is much higher than this peak on the upstroke, and we classify this peak as being this signature as being weight heavy. And so we're doing a lot of extra work trying to lift the weights compared to lifting the rods. And here, when these two peaks are the same height, we say it's mechanically or electrically in balance. And so what happens, though, when you look at this, is that since these two peaks are the same height, then this has the minimum speed change here during this cyclic up and down loading. Here, the speed change is a lot more when you have to do a lot of work. In this case, lifting the weights than lifting the rods, and we see a much slower speed and much more thermal loading on the electric motor. Now, this link here is to that seminar 12 that talks about calculating the neck torque on a pump unit gearbox. And so this is the slide here that shows the conversion from kW into torque. The equations on this report, or this graph that we have inside TAM, and so you don't have to remember the equation, it's just there. But basically it says we're going to convert the kW based on efficiency, pumping speed, and how the speed varies into torque with a conversion factor. And so the red curve is the existing net torque, which is the gearbox rating. This line right here is 320,000 inch-pounds, and the downstroke peak is 228,000 inch-pounds of torque based on kW, and the downstroke peak is higher. It's weight heavy, and so it's higher, 286,000 inch-pounds of net torque, 1,000 inch-pounds of torque. And then in balance, the two peaks would be the same height, 256,000 K inch-pounds of net torque in the gearbox. Now, this is the default analysis, and if you want, you can make some slight adjustments. If you click on that button, this screen pops open, and you can adjust the efficiency of the motor. And we'll see here in a little bit that most NEMA D motors are around 80% or higher efficient, so that's probably okay to leave that number like that. The speed variation, this may be an old slide. I don't know if we can change that now, but this is how much the speed varies throughout the stroke. You can vary the counterbalance, and you need to type in how much the weight that you're going to move to provide the counterbalance. And the software says we need to move the weights inward toward the gearbox shaft center by 5.9 inches to decrease the imbalance. The imbalance is this peak minus that peak divided by 2. That's the change you've got to make to counterbalance the net torque differences on the upstroke and downstroke. And so it gives us a little explanation here, and it's also this is displayed if we go to the report in TAM. Now, this is a very old example. This was back in, I think, 1993 or 1994. And this is a 60 horsepower motor. It's lightly loaded. This plot came out of the Echometer DOS DE software for power. And so I've always liked this plot because what it shows a couple things. It shows that there's two strokes, and it shows that the power signature for both strokes is exactly the same. And it's pretty wiggly. I mean, you would expect if something varied this much from stroke to stroke, it wouldn't be the same. Well, it's the same because the pump fillage, the pump horsepower, the speed is all the same, and so the motor behaves the same. Everything's behaving the same. The other thing that shows is that it's imbalanced, electrically imbalanced. Okay, this peak and that peak are the same height. But a weird thing that it shows is that look at all this extra energy it's generating on the right through here when the motor is right there at synchronous speed, and right here the motor is being pushed by the weights swinging to the bottom of the stroke, pushing the crank faster and make the motor going faster than 12 RPM. It's generating power here and here. So this is your typical conventional pump unit signature for a conventional unit. 2 peaks and 2 valleys. Now notice here that when the current gets to a minimum, this is called no load amps. When the amps get to the minimum, then the power, that means there's no load, and there's no load on the gearbox. So now the power, the kW, is going to become negative, meaning that it's generating power. So this is a good example here just to talk about all those different features about the power signature and the amp signature. Notice that the amps are always positive, and when the motor generates power, the amps go back up. Now, if you were using an amp sensor to try to balance this load, and you're looking at that spike right there, you might say that spike and that spike should line up. Well, that's not true. This and this should line up. So sometimes when you use an amp sensor to balance a unit, you don't pick the right peaks because it's moving so fast. So I prefer, you get a lot better results if you use the power probe to balance the net torque on the gearbox. Now this is a video here, and what it shows first of all the relationship between the net gearbox torque, mechanical torque, and the power. And it also shows that we're moving through many strokes, and this is a full card, and as we pump, you're seeing the surface stroke and the downhole pump, and you're seeing that as we move from stroke to stroke, the horsepower is going to change, and this net torque in the gearbox and the power is going to change because now the pump is not full, and you have less power being spent to pump the well, and you're going to start to see a change in this plot. Also, you see the voltage throughout the stroke and the relationship between voltage and current. And when the voltage goes up, the current typically drops. Less current being drawn, voltage goes back up closer to 480 volts. And so this is a good example that compares power to net torque and volts to amps, and it's an interesting plot. You can see the relationship. Now, a motor has to provide power or torque to when the unit is off to start the unit and accelerate the pump unit. And the motor, a NEMA motor, has a high starting torque, 2.7 times more than the nameplate of the motor. So if you have a 30 horsepower motor, it acts almost like a 3 times larger motor and outputs almost 3 times more power to make the motor make the pump unit start to move. The bigger the load, the bigger the unit, the bigger the motor needs to be to provide the energy to move, to pump the well. And this is conventional pump units. We talked about that already. It has 2 peaks and 2 valleys, and each type of pump unit has a different net torque signature, and you can tell the type of pump unit based on the net torque curve because it's impacted by the phase angle, it's impacted by the type of pump unit. And when you have the torque balance on the upstroke and downstroke, then you're going to see the same thing about the power. The power is going to be balanced, and you'll minimize your energy use because you reduce your thermal load. The thermal load is the current going through the motor causing the motor to heat up. And by reducing the peak torques that you have on the electric motor, the power is then reduced because they're very much related. The power motor provides the power the pump unit needs. And by reducing the power, then you reduce the current flow through the motor, and that's going to reduce the thermal heating of the current flow. Like a toaster gets hot when you turn it on, well, the motor gets hot too when the current flows through it. So if you reduce the current, you reduce the heat losses, and you'll save power. Now, if the polyrod horsepower changes, like we saw in that previous example, based on pump fillage, then the balance conditions are going to change. So when you have a high fluid level, you need to make sure that the unit's not overloaded and being damaged. And then when you draw the well down, you need to, again, make sure that the unit now has lower fluid level and more rod torque. You need to make sure that the well's not overloaded then. So in some fields, you have to move the weights when you first set the well up because you don't want to cause damage. And then it may take a long time to draw it down. And once it gets drawn down, you may have to move the weights again to prevent overload. So this is important. And if you don't do that, then you can damage your pump unit and reduce the life of the gearbox. This is a plot from some Robinson Myers motor performance data versus RPM of the motor. And what it shows you is that when you first turn on this is torque. When you first turn on, or KW, the motor, there's a thing called the breakaway horsepower or breakaway torque. And the motor quickly, this doesn't show time, but it goes from 0 to 600 and faster RPM, quickly speeds up. It goes from the breakaway torque, pushing hard, 2.7 times or more times the nameplate of the motor, and it reaches a peak torque or peak KW. It's called the breakaway torque, and then the required torque to keep the unit going is reduced, and then the motor tends to operate in this range right here. And then for conventional unit, you'd be maybe generating motor energy at the very beginning of the stroke, and then you start to provide power to lift the rods and provide power, and the KW is going up and the motor slowing down. And then you get about halfway up, and then the power required is reduced, and then you get to the top of the stroke, and as the weights fall to the bottom, you generate power, and you're going faster than 1200 RPM, and that's a negative KW that then goes out on the power line, and then the power company sells it back to you on the downstroke. That if the meter's right there, and you got to pay for your own generated power kind of to lift your weights, and then again at the bottom of this, when you're at the bottom of the stroke, then the weights swing to the top, and you usually generate less power at the bottom of the stroke versus the top. And that's the way the motor behaves and the power behaves throughout a stroke. Now the current is a little different. There's a thing called locked rotor current. And if you were to set the brake and turn the motor on, then the current is a maximum, and it doesn't really drop off if the motor is locked with the brake. But if it's not held with the brake, then the amps quickly drop from the locked rotor current down to this normal speed here. There'd be no load. Low load's a minimum current, and then the current increases to lift the rods, and the motor slows down. And look, the amps that you're using goes above the rated amps for burning the motor up. So during the peak use of amps to lift the rods, often the amp draw is above the motor rating. But as long as the RMS use of current during the stroke doesn't stay above the motor rating for amps for heating, then the motor cools back off, and then it goes back on the downstroke, and so it kind of operates this way: upstroke and then downstroke, kind of like that. And the speed's changing all the time throughout the stroke. Now this is a plot from TAM analysis plot of the instantaneous strokes per minute. And so where that comes from is we use the accelerometer to get the position on every sample of the polyrod, the position of the polyrod, and that also then we calculate with the geometry of the pump unit the change in crank angle and we compare the crank angle to the total 360-degree stroke, and that gives us the strokes per minute right here, and we're calculating the strokes per minute, instantaneous strokes per minute right here. And so we see when the power goes up, lifting the rods, the motor slows down, and then the motor speeds up when we generate power, and then when the power is below zero, and then again lifting the weights, the motor slows down, and we see a drop in SPM, and that's the normal behavior, and that's called motor slip. And a NEMA D motor is designed to slow down when the peak torque occurs and slip and not draw as much current. If you had a different kind of motor called a NEMA B motor, then the NEMA B motor wouldn't slow down as much, and it'd draw more amps, more current, and it would thermally load the motor, and it'd make it easier to burn the motor up. So NEMA D motors are designed for cyclic loading. They slow down and speed up throughout the stroke. As you can see here, there almost is a 1 stroke per minute change. Yeah, it's about from 8 strokes a minute to 9 strokes a minute. During one stroke, it changes 1 stroke per minute as the load on the motor changes throughout the stroke. So this shows us what motor slip is. Now, we've kind of talked about how the motor works, and we've talked about that how the breakaway torque and breakover torque to accelerate the pump unit. We've talked about the signatures from each type of unit pump are representative. Now, we haven't really talked as much about something called cyclic loads. The cyclic loads is how the torque varies throughout the stroke. And the cyclic load change, once you balance it, represents the change in energy use. So when you compare the cyclic load unbalanced to balanced, the change in the cyclic load is approximately equal to the amount of that ratio that is a percent change in your power use. And this sentence right here is probably my favorite sentence in this presentation, is that the gearbox demands and the motor provides. And so there's this relationship. If the gearbox says motor burn up, the motor's going to do what the gearbox says. Unless the motor's protected, it's going to burn up. So they're very much in a symbiotic relationship. I don't know if the motor gets much from the gearbox, but it does exactly what the gearbox needs. And we can easily tell unbalanced versus balanced because the peak on the upstroke or downstroke will be higher on either one if it's not in balance. This is the startup motor power consumption. Now, what do I mean by that? Well, look, we did a valve test right there, and the motor's off, and the kW is 0. And we turned it on right there to start it back up, and then look, there's a whole lot. There's the breakaway and breakover kW right there, and then quickly look, it's reached in this short of time. The motor's acting normal, so it doesn't take very many seconds at all, maybe even less than a second to be under normal operation. And this extra power here it uses to start the unit, it's about equal to the amount of power used during a stroke. So here's the power used during a stroke, positive power and the negative power, and that energy right there is about equal to that right there. So why am I telling you all this? Well, if you have a pump off controller or percentage timer, and you turn on the well every 15 minutes and off every 15 minutes, on and off every 15 minutes, then what that means is that you're starting and stopping at like 96 times a day. And if you save 1 stroke, that's equal to the power used to run the well during 1 stroke to start it up, and you save power by not running your unit all the time if your pump's not full. Try to run it full, efficiently full, and then when the pump's not full, turn it off. And sometimes people say, well, you waste power starting it up. Well, as long as you save 1 stroke, it offsets that power. All right. So I took this right here and I blew it up, and here's it blown up. And I said, you know, it is, if you look at this right here, this is your breakaway and breakover kW, and this is less than a second. And if you look, this is a 30 horsepower motor that's equivalent to 22 kW. You multiply that times 2.7, and that's 60 kW, which is about you know, 3 times bigger. That's what I was trying to say. This number 60, that's 60 right there, is 3 times bigger than the normal kW of the 30 horsepower motor, and that's because it's a NEMA motor. Another motor would be less. Now this is the polished rod load, and this is the position, and this is the kW and the amps and the volts, and here we are stopped for a valve test, and the power drops to 0 and the current drops to 0, but Ken put when he disconnected the power, he put the clamps above the HOA switch for volts, and we can see the voltage on the line. And so when we turn the motor on, we see this big drop in volts from like 480 down to like 300 and something, not, you know, 320, big drop. And why is it dropping? Well, the transformer where the energy is 480 is far away, about half a mile away, and the energy has to flow through the line to the well, and you see a drop in volts at the pump unit, and the volts over at the transformer is still 480. So this is called line loss. You can use this to calculate the line losses. And so this kind of talks about how you do the line losses and shows the current, and it shows the voltage, and we can use this to calculate the line losses. And so it's the voltage starts at 480 and it drops to 488, drops to 340 during starting, and then we can use that to calculate the line losses. And the average kW for a stroke is 16, and you have the input's about 9.7, and there's your line loss is 0.08 divided by 10.5 volts, and that's about 7.6% of your power bill. So we're losing about $57 per month for power line losses. And if the wire was a smaller diameter wire, then we have a lot more line losses, and it might justify changing out the wire. But in this case, the wire's not too small. We're not wasting too much power. Now, here, this is the same plot as before, but now I'm talking about average current compared to RMS current. And when you're in balance, look, the average current compared to the RMS is the minimum. That means you have the least amount of energy lost to heat. And then when you're out of balance, there's more, you know, the RMS is squaring all these values and then summing them up and summing them up and then taking the average and then taking the square root. And the far away from the average you are, the more energy is being lost to heat. So when you balance the unit, all you're doing is you're taking the RMS current and pulling it closer to the average, and you're reducing your cyclic load factor for kW, and that's equivalent to a reduction in heating. And so here we're reducing our thermal current flow by reducing our RMS current. That's what this is trying to show us. Now this is a well. The name of the well is called Burn Up. And this is a well up in North Dakota, and I think Ken and I were there a long time ago, back in the 1990s. Is that a long time ago, Gustavo? Before 1997, when you were in high school. Anyway, there was a NEMA B motor on the well, and it was a 40 horsepower motor. And we hooked up the power probes and did a dynamometer on the well. And I was excited, and I said, wow, look, the thermal loading on this motor is 91%. The motor's going to burn up. Well, I was thinking, cool, we get to talk about cyclic loading and thermal loading and all this kind of stuff. And I found a real example, and I was just kind of jumping down probably. And I said something dumb. I said, well, why don't we wait till the motor burns up? And the electrician wanted to shoot me when I said that. I didn't realize I said burn your motor up, but I kind of said that. And of course, I was kind of like, they have to do what I say. I didn't realize that either. And I said, change it out to a 30 horsepower motor that burns up, and then we'll see a lot better performance with a 30 horsepower NEMA D than a 40 horse NEMA B motor that's a different type of motor. It's not designed for cyclic loads. And so when you look at this current right here, the red line, notice that the current's going almost to 100 amps. And once we change out the NEMA D motor, the peak current's less, and the thermal load here is less. It's 58% of the motor rating. It's less, and so in effect, by using a smaller NEMA D motor, we got a better, for the same well, we got a better performance. We got less thermal losses, less energy loss to heating, just by picking the right kind of motor. So this is a good example that compares a NEMA B motor to a NEMA D, and the NEMA D slips, whereas the NEMA B doesn't. It's more stiff. It has a lower starting torque and a higher thermal load and less efficient. Now, so what motor do you use? Well, you can use what kind of a prime mover you use. You could probably use an electric motor or gas engine. And the electric motors are better than gas engines because they're cheaper and they take less maintenance, and they can be totally enclosed so they're all weather service, and they're easy to turn on and off, so they're good for automation systems. Now, the gas engines are better than electric motors because they have a flexible speed of throttle. They can change speed just by giving it more gas or less gas. Less RPM, more PM by giving it more. Anyway, step on the gas. You can operate over a wide range of conditions because you usually have a big flywheel on a gas engine. And you can use the lease gas, which I've been told is not free, but you have to pay the operator for, the owner of the lease on it. You have to pay royalties on it typically, but you don't have to pay the power company any electric bill. So which one do you use? Well, you use what's available locally. If the well doesn't make any gas, you can't use a gas engine. If you can't set power poles because it's in rock, hopefully you use gas, not electric. Maybe you don't want to have a mechanic or don't want to have an electrician, so you don't use. If you want to have an electrician, you have electric motors. If you don't want to have a mechanic, you don't have a gas engine. And maybe your boss comes in one day in the office, and he takes his hard hat off and he just throws his hard hat across the room and says, "We'll never use one of those blankety blank blank." And he might say electric motors or gas engines one day. You don't know which one you might not like, but personal preference sometimes. All right, so how do you determine what size of electric motor to use? Well, Q-Rod does that. If you run Q-Rod and it designs the pumping unit, the size of the pumping unit, it calculates the net torque on the gearbox. And then we can calculate the average torque and the RMS torque. And the ratio of RMS torque to average torque is called the cyclic load factor for kW. And then we use we take the cyclic load factor times the polished rod horsepower, which is, hold on, let me get that. Polished rod horsepower is right here. Nope, right, where's polished rod horsepower? Polished rod horsepower is right here. Polished rod horsepower. The polished rod horsepower is right there, so you take the polished rod horsepower times that's RMS torque divided by average torque, cyclic load factor, divided by the unit efficiency. And a big unit typically is 95% efficient, and a little unit is not as much mass, so it's usually less efficient, let's say 80% efficient. And that calculates the motor size in Q-Rod. So you design the motor, a NEMA D motor based on Q-Rod using your cyclic load factor from net torque. Now, Bob Galt said, this is a bunch of hooey. And Bob Galt was a famous pumping and design engineer. And he said, just take the polished rod horsepower times 2 and use the next larger size motor, and that's going to be good enough. As long as the fluid level is down at the pump, that will be correct. Now, what did he say? He said, if the well's drawn down and you select the motor that's 2 times the polished rod horsepower, that's going to be good enough. Now there's a reason for that, but usually if we go back and look at this example here, we see that either method typically will work, give about the same thing. So here is the polish rod horsepower, and the motor size needs to be 10.4, but if you take 5.9 times 2, that would be 11.8, about the same number. So either one would say use a 12.5 or 15 horsepower motor, and that would probably be just fine. And so when we run QROD, we're designing a NEMA D motor when we use QROD, and it's designing it based on the RMS torque compared to average torque and the unit efficiency. Okay. Now, when you run TAM and you calculate the cost, here's our cost for cost per barrel of oil, or cost per month, or credit, the cost credited with the generation or the demand charge. All these costs are based on the stroke you select to analyze. Now, it tells us right here in TAM, hey, for the conditions you're at right now, a 20 horsepower worked just fine. Now, what if the fluid level was high? Would you put a 24 horsepower motor on there? Well, no. So if we go back and look at this right here, we're designing this well with the pump intake pressure of 116 psi. We're designing the motor for a low pump intake pressure. And so anytime you use QROD to design your motor, you should probably put in, 50 psi for your pump intake pressure, so you get a big enough motor for when the fluid level is down near the pump. All right. This one says efficiency is around 56%, and this is probably the case here, is probably the pump is full. So that would be the efficiency I'd expect. If the unit is properly maintained and the pump is full, I'd expect to see efficiency close to 50%. Now, what's high efficiency? Well, you should see efficiency over the overall system, about 50%. Half the power you buy should be delivered to the liquid to produce the liquid. The surface efficiency should be greater than 80%. Mechanical efficiency should be high. You shouldn't overload any of your equipment. The equipment should be not overloaded. The reservoir, to be efficient, you should have the producing ball pressure less than 10% of your reservoir pressure. That means you're getting 97% of all the fluid available from the well. And so this would be a high producing efficiency, high mechanical efficiency, and high electrical efficiency. And you can determine that with your Echometer, dynamometer, and fluid level instrument, and power probes. So what do? Well, if you want to analyze to see if a well is efficiently produced, you're going to look at your inflow performance and your fluid level. You can measure the power and look at your overall efficiency based on your polish rod horsepower. You can see if your pump is full of liquid, which is important. A full pump is important for efficient operations. If your pump's not full, it's because there's a gas problem. You need a better gas separator to improve your efficiency. Is your mechanical loading of your unit or pumping unit exceeding the rating of the equipment? And is your motor being thermally loaded? Is it going to burn up? And see, these are all these kind of things you can use to analyze your well. Now this is a picture of the Vogel IPR curve, and this shows that here's our producing bottom pressure divided by static, and this is a 1's 100% and 0. This is a static producing bottom pressure equals 1, and then here the producing bottom pressure is 10% of the static, and if you operate with the producing bottom pressure 10% of your static or less, then the Vogel curve says you're getting 97% of all the fluid of the maximum flow rate available from the well. So that's why we say that's your efficiently producing reservoir when you have your producing well pressure less than 10% of static. That's based on a Vogel inflow performance curve. Now here we're looking at one of our examples. This is an example that we'll look at in a little bit. And I'm just showing you that if you're below 0 here, you're generating power. I talked about that before. I could have probably skipped this slide. We're going to talk a bit more about efficiency. We're going to talk about surface inefficient. We're going to talk about using your fluid level and dynamometer survey to analyze your well. We're going to talk about how to identify low efficiency problems. So here's Everybody likes equations. So here's the hydraulic horsepower equation. What does that mean? Well, it means that if you were to take some liquid down here, and you start from the surface and you raise the liquid to this from the liquid level up to the surface, that's called the net lift. And you took 1 barrel of liquid per day, that's a barrel per day. You have to multiply it times the specific gravity of the fluid to get the net lift. Okay, and that becomes the hydraulic horsepower required to lift a barrel of fluid to the surface. And you divide by your input horsepower, and that becomes called the system efficiency. And so this is an equation that's been around for a long time. We're talking about raising the fluid from the liquid level up to the surface, and if you had 1 hydraulic horsepower is 27 barrels a day from 5,000 foot. Now here's our barrel, and we lift it up to the surface. And the reason why I'm kind of hem-hawing about this equation is because we're assuming that this liquid on the outside of the well bore and on the inside of the tubing is exactly the same if you use this equation. So Jim McCoy and Jim Lee and I argue with Jim Lee about this because he had written a paper, and we argued that this equation doesn't work. And we wrote a paper on it. So the paper reference is attached at the front of the paper, in the front slide. All right, now here's an example that's going to show why that didn't work. Look, here's our kW for a stroke, and we've measured it with the power probe. And this is a well that was measured on, and the fluid level is only 94 feet from the surface. So is the hydraulic horsepower not very? Is the system? What's going on here? You don't have to lift the fluid 100 foot. Well, that must mean the well's 100% efficiency almost, because you don't have to lift the fluid very far. Okay, so that's kind of weird. Now, hold on. The pump intake pressure is about 730 psi, 700 psi, and the tubing fluid gradient is 0.33, but the annulus gradient is pretty light. It's pretty light, so we don't use the gradient, the fluid in the annulus, gradient of fluid in the tubing to calculate the hydraulic horsepower. And so when Jim McCoy and Jim Lee and I were arguing about the hydraulic efficiency, the system efficiency of a well, we said you got to take into account the gradient of the inside and the gradient of the outside of the fluid. So you need to work off the pump intake pressure and the tubing fluid gradient to come up with the correct hydraulic system efficiency and the correct hydraulic horsepower. And so if you're interested more in this, then you ought to, but this is a method that TAM and TWM are supposed to use when we calculate the system efficiency in the software. So look, if you look at the pump intake pressure divided by the tubing gradient, then the net lift is 2,880 feet, not 94 feet, because the pumping system has to lift the fluid from the pump intake pressure to the surface, not from the liquid level top to the surface. And so you need to know what the net lift is calculated based on the actual tubing fluid gradient here. So this is saying the system efficiency of this well is about 50%, and that's what we think. But a lot of this liquid that's being produced in this well is flowing up the casing annulus, so I'm not sure it's 50%. But this is an example we'll look at in a minute. The efficiency is pretty simple to measure. You can compare it to cost. If efficiency is low, indicates a problem, and we should be looking at the efficiency of the system, both the surface and the system, to see if there's a problem in the well. If any one of these pieces in the well goes bad, then the system efficiency is impacted by multiplying that efficiency by all the other efficiencies. So what am I saying by that? I'm saying if the motor becomes 50% efficient versus 80, it impacts the overall system efficiency significantly. Each piece has a big impact on the efficiency, and all these little different pieces need to be efficient. Now this is the motor efficiency for NEMA D motors, and this is the motor output horsepower. And we can see here that over most of the range of the motor output horsepower, the NEMA D motors are 80 to 90% efficient. And if you look at a 60 horsepower motor, you can see that the peak efficiency is around, this is 60 horsepower, is around 30 horsepower. And so when Bob Galt said take the polished wood horsepower times 2, he knew that if you multiply this times 2, you get the motor rating. And you get the most efficient motor size if you take the polished wood horsepower times 2. So this horsepower, the most efficient operation, is half the motor rating. And that's what you typically see. And you could use the output horsepower here as a polished rod horsepower, because there's just a slight loss of horsepower from the motor output to the polished rod, only maybe 5%. So we went out and measured a bunch of 60 horsepower motors, the polished rod horsepower and the input horsepower, and we calculated the ratio between the polished rod horsepower divided by the input horsepower, and we found that all of those wells had a surface efficiency within 10% of the motor performance curve. And so I said, hey, we ought to look and see if we ever find a surface efficiency on a beam pump system that's less than 10% within the nameplate, the published efficiency of the motor. And so Elton Smith went out to a well in Seminole and acquired this data on this well. And he called me and said, hey, I found this well has 67% efficiency on the surface. And I said, that's great. I said, crawl up the ladder and touch the back of your hand to the tail bearing. And if it's hot, you found a bad bearing. And he called me back hollering, cussing, and said, you about burned my hand off. And I said, that's great. We found the problem. We found a bad bearing. Turned out that the manufacturer problems with tail bearings on marked pumping units. And we found it by what? By measuring the power and looking at the polished rod horsepower. So this is what this shows right here. And we've got an example that'll show us that. This is the before data. This is a bad tail bearing. Here's our efficiency. Here's after we repaired the cross-rope bearing, the tail bearing, and the efficiency is 83%. And so this is an example that we have in the TAM examples. Now you can use the fluid level, the dynamometer card, and the power to see if you're what's the problem with your well. And so we published this in a technical paper talking about electrical power. And it says if your bottom pressure is low and your pump is full, then you don't have much you can do downhole, so look for the surface if your efficiency is less than 35%. Maybe you have a tubing leak or something else. But anyway, if it's less than 35%, look for your surface problems. If you have low bottom pressure, the pump's not full, then look at maybe do something control runtime or fix this problem at the pump. If your efficiency is less than 35% and you have a high fluid level and low pump failage, then it's probably gassy. It's gassy well, got gas interference, and you need to get the gas out of the pump. Well, if it's greater than 35% and you have a pump that's full, then the well's okay. If it's efficient and there's not that much you can improve to get it much higher. If you have a high fluid level and the pump's full, then you need to look at increasing production out of this well. If you have a high fluid level and low pump fillage, even if you're greater than 35%, you probably ought to get your gas out of the pump and look at your gas separator. So what do you do to minimize your electric usage? Well, the number one thing is to maintain a full pump. You know, you need to match your pumping capacity with your wellbore inflow. If you're pumped off, then consider a variable speed drive, a pump off controller, or timer. If you have gas interference, run a properly sized gas separator at sufficient capacity. When the system efficiency is low, find what's wrong and fix it. If you're out of balance, balance the pump unit. Now, not only balance the pump unit, but you ought to maintain the pump unit. Probably every year or every 6 months, the unit ought to be maintained and cared for and serviced to keep it in top-notch operating conditions. Don't use a giant pump unit to pump a little bitty load. Make your unit match the requirements of the well. And when your motor efficiency falls less than 50%, it's a waiver-sized motor, service efficiency drops really low, then you can reduce the motor size. But be cautious about changing maybe one motor size, because usually the motors are about the same efficiency, and you may not gain much just by changing a motor out from one motor to the other size. If you're going from a 40 to a 30, if it's both NEMA motors, are both going to be about the same efficiency. You need to make sure that your pump maintains proper operation, is filled with liquid. Make sure your volumetric the pump displacements are full, and when it's not, you need to make sure you control runtime to pump a pump with a full pump. Low efficiencies are caused by incomplete pump fillage, so make sure your pump is filled with liquid. Make sure your gas separator is sufficient capacity to maintain a pump displacement filled with liquid. And when you have excess pump capacity, control your runtime. If you maintain high efficient operations, you'll have your number one cost or number two cost reduced. Reduce your power cost. You'll reduce your mechanical operating expenses. You'll increase your oil and gas production. And you'll have a lot longer time between failures. And so that's the end of this presentation right here. Any questions or comments?
Yes, Lynn, thank you for that presentation. And we do have a few questions here. One is in the public chat, and it's from Johnny. He said, well, Johnny says he's used to use these tools a lot in his field, and he's very well familiar with how they work and what the reports can tell him after he runs the test. But his question is there a way that the Echometer software can simulate or estimate the electric savings per month, given the current power usage, the dyno car, and the recommended counterweight movement for balancing the unit? The only way he knows to do that or estimating the cost saving is after he runs SROD design.
That's a really good question. And let me see if I can get TAM to pop up here. There you go. So if I go into TAM, and this is an example. Let me show you the examples here. Pick a well, and pull this over. Let me just pick this up. All right. So here are the examples that are in our examples, and this is a reverse mark that is balanced, and I need to find one that's not balanced, but let me just pull this one up and show you. If I go to this one that we measured power and it's balanced, and if I were to go to the report and I look at the report and I look down toward this part right here, now this is your torque report, okay? And if you look at the cyclic load factor, okay, this is a cyclic load factor before and a cyclic load factor after. And the net torque and the kW, or I'm going to say something that's not quite right, are exactly the same relationship. And so if you compare the change in net torque from RMS torque to unbalanced to balance, existing to balance, then this ratio, this reduction in this ratio of about, not very much because it's already balanced, from 1.256 to 1.254, that's a 2, there's a 0.002, that ratio of 0.002 to that number right there would be how much power you'd save by moving the weights in this case. Sometimes it's a lot more significant. So this would be the amount of power you'd get in this case by balancing it, but it's already balanced, so you're not going to save any in this well. If we go find another well, you'll see a lot bigger change in the cyclic load factor, which means a lot bigger change in the kW per stroke.
Okay, thanks, sir. So let's take an extreme example. Let's say my existing factor is a 3 and my imbalance would be a 2. I would then expect a 50% decrease in my electric costs month over month, if I'm understanding you correctly.
I don't think you'll see that big a change, but yeah, I mean that would mean you'd get a 50% reduction in power. Well, that would be 1 compared to 3, because this is what you're doing now, and this would be what you'd be using in the future. So you'd save 1 out of 3. So it would be a 33% reduction, I think.
Okay, all right. Thank you, sir.
Yeah, we just never done it. We never published this, but this is. I can send you a paper that's written on this a long time ago that kind of discusses this idea.
Thank you, sir.
Next question.
Yes, we have a few more questions. There's a quick question here regarding, can these measurements be done when you're using a VSD?
That's a good question. I didn't put any VFD examples. I should have. I forgot about that as an issue. One of the problems with VFD is on the outside of the VFD, the power is normal. On the inside of the VFD, between the VFD and the motor, the power has changed. And if you measure the power on the outside, then that's more representative of what's really going on that the power company sees. If you go into the inside, then the frequency's changed, and you can't really use it between the VFD and the motor. So I'd say you have to measure it on the outside of the VFD. Now, a lot of VFDs have resistors on top of their variable speed drive, and whenever you generate power, then the power goes back in the VFDs, and the resistors at the top of the VFD get hot, and fan blows that energy away, and so that energy, that regenerated power is wasted. So it's important I guess I should have just answered your question and said it's important that you put the power probes on the outside of the VFD if you're going to try to study the power use.
Okay. On slide 26.
Okay.
We have a question regarding the efficiency. He's asking, can you tell us more about why the efficiency or the system efficiency is higher when using a 50 horsepower NEMA B motor compared to the 30 HP NEMA D motor?
This slide here.
Yeah. So it's talking about the system efficiency, 84% on the NEMA B.
You know, I don't know. I don't know. I can't answer that very well. I don't know why it shows that. We have the data we can look at in more detail. I don't believe that number. Basically, I need to look at it more. I just don't know why it's like that. But that's a good question. If the fluid level is higher in this case right here, maybe that's why it's higher. If we look at that data, maybe it'll tell us. But the truth is that this installation, the justification usually for buying a NEMA B motor is that usually are a little bit their efficiencies is a little bit higher than a NEMA B motor. But due to the thermal loading, they use more power because of the cyclic loading. And so normally the NEMA B motor, even though it's rated with a higher efficiency, often than a NEMA D motor, it's going to be less efficient because of this thermal loading is close to the rating of the motor. There's more heating's going on. So I don't know why this number is higher. It shouldn't be.
You should expect the opposite, right? The opposite.
I'd go back and look at the pumps and we can look at the data, but it should be 50%, and this should be lower than 50%. I'm not sure why this data we got back in 1993 or 1994. It's been a long time ago. I just don't know why it's like that.
It's been a long time. Yes.
But it's not. It's. I don't think it was bad. I just think there's a reason, like the pump fillage or the fluid level or something like that is different.
Okay. On slide 44, we have another question, and the question is, what do you mean by surface losses? On the left-hand side, we have surface losses as the motor and the unit losses are being considered. Is this a stuffing box friction on the left-hand side?
Well, we discussed that, and we said, well, maybe it's the tubing pressure, maybe it's the stuffing box. But if you read the paper, this is right out of that paper that. Let me go find that paper reference. I don't remember the reference. I'm going too slow. Let me go back to the paper here at the very beginning reference. It's Carrie Ann put that on the package you can download, the bundle, and this is the paper right here. You ought to read that paper, and hopefully we define that. If it's not, it should be in that paper. But I think it's the tubing pressure and possibly stuffing box friction.
Okay, I have one more question here. It says on slide 24.
Okay.
Not too far. So the first line that says line loss, that states from above, the 0.8015 kW, where that comes from.
Oh, well, good question. It doesn't show it, does it? So this came out of the paper. So we discussed how to calculate it in the other reference paper, the 2015 paper on power. And so it references this slide right here. And if we go into that paper, I just stole it right out of that paper. And I should have put more detail there. But actually, Jerry West was a primary author of the paper, and I just put that on the slide. So if we go back and look at that reference, it's this one right here. And this paper right here is for the wireless power probes. We started measuring the voltage, and once we measured the voltage, we can calculate the line losses. And so if we go, I probably should have put that on there, but I didn't put it in there. It's in this paper. And again, if you read the paper, look at the paper, it talks about how to do it. But the main thing I wanted to try to explain was the idea. The drop in the voltage occurs between the transformer and the pumping unit. And over at the transformer, let me see if I can't forget this. Over the transformer, the voltage is around 480 volts. See this right here, it's 480 volts. And then when you kick the motor on, you have a big inrush of current, and you have a big drop in the voltage right there at the pumping unit, and you're trying to flow that energy from the transformer to the pumping unit, and that's the voltage loss, and that's what represents the change in voltage over the wire from the transformer to the pumping unit. And the bigger the wire, the less voltage drop you're going to have. And that's really the idea I wanted to talk about, but the equations are discussed in that paper. So if you're not satisfied with the answer, email us and we'll give you more information than that. Our eventual plan is to put that calculation inside of TAM. Whenever you do a valve test, we'd calculate the line loss. We just haven't done that yet. So that's a backlog. That's a backlog that we need to put in TAM.
I have one more question from Juan Carnaque. Well, I'll try to get back with him. I don't fully understand the question. So please go ahead and start with examples, and I'll come back to you later.
All right. So this example right here that I picked, I wanted to start off and show you a reverse mark. And I picked this reverse mark, but it doesn't have power. And I wanted to show you the torque curve, the net torque curve, and I asked Ken Skinner if he had a good reverse mark data with power data, and he had. But it's not balanced. So if I go to the report here and look at the torque, there's no power here, but let's look at the torque. This reverse mark shows a big hump in the middle, Okay, now that's the signature for a reverse mark. A mark unit has a spike in the middle, and notice how the reverse mark has the two lifting the rods, lifting the weights. It looks like a conventional, but right here in the middle, this is flipped over, and there's not very much power generation. And usually, when the unit matches the well loads, then you minimize your thermal loading. Let me show you what I'm talking about. So if I go look at the data that Ken got, that provided to me, this one is a great example where the pump is full. This is a well up in North Dakota. If I go to the report right here and scroll down to this part right here, this is what I wanted to show you. Look how the torque is it's not exactly, but it's almost constant. Okay, and look, and what that tells us is that if the motor is providing a constant power, then the energy, there's no thermal losses. It's almost very efficient. It's a very efficient system as long as the motor is sized properly. And so one of the benefits of the reverse mark, the torque master type unit with the phased crank and a conventional geometry, is that if you select your unit properly, you'll minimize your power cyclic loading, and you'll have almost a constant load, which means a high efficiency. So this is what I wanted to show. This was one little graph here. And again, look, there's a big hump in the middle. That identifies the reverse mark. Now, what am I saying? I think these units have the potential to be very efficient. You know, and it's because of this hump, and that you can see that almost constant power, and that's a good feature. All right, now let's go on look at another unit. That was the reverse mark. I want to show that one thing. Now, the lightly loaded motor is in a CO2 flood, and the pump card, it's just gas compression, so the pump's not very full. But the operator, and it says we're not producing any fluid because this is all gas compression on this stroke. But if we go look at this power use, the power use plot, let me go look at the power use into the report, and let's go down to look at the very last page here. You know, it's balanced, and this is the same. This is the one where I show the two strokes side by side, and the efficiency is really low. Well, it's 37%. So why is it low? Well, it's low because it has any efficiency because the well's filling up the casing because it's got a very high fluid level, but it's low because it's got a 60 horsepower pump unit only doing about 10 horsepower work, and so it's 1/6 of its rating. So if we were to go back and look at the presentation, back at that, let me go find that presentation and go look at this efficiency plot curve right here. If you look at this plot, geez, where'd it go? If you look at the efficiency plot right here, this one, notice this is a 60 horsepower, and if you take 10 horsepower or 7 horsepower, the efficiency curve is really starting to fall off, and you start to get out of that 80 to 90% efficiency of the electric motor. So when the motor is lightly loaded, not very much work being done, then you can change the motor out and save power. But if you change, here's an example. This is a 15 horsepower right here motor. If you change to a 7.5 or 5 horsepower motor, they're going to be less efficient than a 15 horsepower motor because it's a small motor with not much mass. Okay, so here's a 15 horsepower motor that's up in the 80 to 90% efficiency range over half of its nameplate. But these 5 and 7 horsepower motors are much less efficient. If you were to look at the 60 horsepower motor right here, and you would say, well, let's look at a 25 horsepower motor, they're both pretty efficient over most of this range. And so the 25 horsepower motor and the 60 horsepower motor are fairly efficient, and you have to be a lot less. You have to be lightly loaded before you gain much efficiency by changing out the motor. And that's the point I want to make with that data right there. So let's go back to TAM. So if we go back to TAM and look here, even though this well is very lightly loaded, the motor's lightly loaded, the pump, there's almost no horsepower being done, the motor still is difficult to justify changing the motor out. For sure, when the water cycle hits the water flow, this is the oiling, this is a WAG, CO2, and then water injection cycle. When the water hits, it's going to be a lot of work required, so they can't change it because of that. But again, it's hard to justify changing an electric motor unless the motor is very lightly loaded and not doing much work. Let's pick one more example here. We talked about the bad tail bearing. That example's there. I think I said what I needed to say on that one. The motor burnup, I'm still not sure why that said 80% versus 58% efficiency. So this is the NEMA D 30 horsepower motor, and this is the this is the NEMA B motor, and you can see here that this pump card is pretty small, and also it's not picking the right place right there. I suspect that the way we acquire the dynamometer data caused the surface loads measurement to be too small. And so if I go here and look at this right here, it says it was an HLT, and that's a Lutert dynamometer that we used. And so I think the problem is that the Lutert measured loads are off. That would be the reason why it's calculating at a high efficiency. Okay, because but here it says the efficiency is 46%, and then the fluid level is pretty high, and so it's producing 313 barrels a day, and that's why this horsepower is too small. It should be closer to a lot higher. This should be 80% and not so low, and it's too low because this dynamometer card is probably not the correct loads, because it's a Lutert that has some hystereses in the loads. That would be my answer to that question, Gustavo. It's because we didn't use a horseshoe load cell. Okay.
It's a Lutert. Yeah.
All right. Ken and I went out to this well, the V11 well, and we hooked up the power probes in different ways. And so if we go look at the dynamometer data here, and we look at the power analysis tab, this is what it normally looks like on the V11 well. We see that it is weight heavy. This rod KW curve is lower than the KW curve. The KW curve on the downstrokes, there's KW, upstroke, downstroke, generation power. This is what it normally looks like. And so let me go to the first one, which is, I picked on the history tab and go down here. Okay, this one is we're not measuring the right voltage, and I'm not sure what we had. I think the adapter was bad, so I think this fixed power adapter was bad or something was wrong. But anyway, there's a problem here. If we go to the next tab over, this one is probably okay, and then this one is okay here. Okay, now the left current clip is upside down, so there's two current clamps, and the left one we turned it upside down on purpose, and now the voltage is wrong. It should be the two peaks and a valley in the middle. And if you see this, something like this, on your data you collect with a power probe, then this shows that we had the current clip on the left side upside down. Now, if we go to the next one, it says the right clip is upside down. It looks like this. Still the power's all messed up. Okay, so there's it's not connected correctly. And if we go look at this one, the left voltage clip. Okay, there's three phases of volts. There's three red alligator clips, and the one on the left side is not connected. And so the voltage the kW is about half as big as it should be. And so anytime you see the kW curve that looks unusual, check your connections, check how the power probe is connected. It won't burn the power probe up, it just doesn't show the right data. This one, the center one is not connected, and you can see again it's a little less amplitude right there. And this one, terrible. The right voltage clip is not connected, and it's going off the screen. It's plotting off the screen. So this is another example. And I think this last one is probably okay. So my point here is that you may want to go if you use a power probe, you may want to go to your wells and try hooking up the power probe wrong and collecting data to see how your normal well power looks when the power probe amp sensor clamps and the voltage connectors clamps aren't connected properly to the panel, because it'll impact typically the kW plot. And then if you see that sometime on one that you collect, you'll know what you don't have attached properly when you're trying to acquire the power data. Okay, so that's what this example shows. All right, so we talked about how you can use the power probe data in the first hour or so of the presentation, and then we've got, I think, 8 really good examples that show different problems. And then what we want to do next is we want to talk about how to acquire the data in the last 25 minutes. And some of the slides I've already shown, so I'll probably skip over those. And Gustavo, if anybody types in a question, go ahead and interrupt me while I'm talking. We can do that, okay?
We have one question now.
Okay.
On this power measurements, are these measurements applicable to hydraulic units?
Yeah. If it's got an electric motor, we've collected power on electric motors for the Dynapump and the Lufkin hydraulic pumping unit, and yeah, there's not any reason why that won't work. In fact, the presentation I did at ALRDC, I think last year maybe, in the sucker rod part, we talked about inefficient pumping, and we use the power probe to show that. So the power probe is an excellent tool when you're trying to analyze hydraulic pumping units, because if there's no counterbalance, then normally the efficiency is very low. You have to put in a lot of power to lift the rods and the fluid load, and then there's no power required on the downstroke. It just falls down. And so the counterbalance is important, and that's why pumping counterbalanced sucker rod lift wells are efficient, 50% efficient. If they're not counterbalanced, they're maybe 10% efficient. So you need to, if you have hydraulic pumping units and your power bill you think is too high, you need to be measuring power when you do a dyno on those wells to figure out why and which wells are inefficient. And the power probe will help you figure that out. So that's a really good question, by the way. Yes, it's a very important.
That's all we have.
Okay.
Go ahead.
Okay. So if you are in TAM and you want to use do a certain test, if you click on the Help tab, then this how-to is in the Help. And so if I go to How to Use Power in a dynamometer test, and you click right here, the presentation I'm going to make is, well, this is different, but this is how to acquire power. It's shown in the Help. All right, so let's go back to the how-to. This is the how-to. It's on the web page. You can download it. It's a how, and we've already talked about what you expect to learn from analyzing the power data you collect on a well. And these are the questions you need to ask when you collect the data. And this is the wiring harness with the radio for the portable wireless power probe. And here we have it inside the panel. And you can see that we have the radio attached to the panel, metal panel with a magnet. And there is the left, center, and right adapters connected. And here is the current sensors attached. And it says left side, and it'll say right side, and it says this side up. So that's connected properly. But if I had to connect this, you're going to disconnect the power at the top before you connect it. But I would probably put these 3 voltage sensors up here above the HOA switch. So when the HOA switch is turned off, then we are able to bring in the line power, and we'd see the 480 volt power, and then we would see the drop when we did a valve test, and then we turn the unit off and on. We see that the sag and the voltage. So you can't see it here because you're past the HOA switch. So I probably wouldn't hook it up there. I'd hook it up here above the HOA switch. So when the HOA switch is off, you'd still see the voltage up here. And it says don't exceed 750 volts. The wired power probes, I think, are rated for 480. And the wireless one goes up to the next higher voltage rating. So 300 amps and 750 volts. If you look here, you can see that the switch is up. That's the main switch. And we're disconnected. You should visually inspect to make sure that those teeth are out and it's not connected before you put your hands inside the panel to connect it up. Before you even open the door, you should have a proximity detector and wave it over the panel and make sure the panel is not hot. Or check the panel with an amp meter. A voltmeter. We include that in the wired equipment when we send that out. If you don't have a proximity voltage tester, you can get one at a local supply store. Ken, how much do those usually cost?
20, 30 bucks.
Okay. Yeah, so you should get those, and always check and make sure that there's no loose wires. When you open this up, you should look for rattlesnakes and cottonmouths and all kinds of snakes, and don't get bit by a snake. Don't get bit by a black widow spider. Look for wasp nest. I think Ken usually carries a bug repellent spray can with him when he opens it up to kill all the bugs. Don't get bit by something. Watch where you stand. Don't stand in a puddle of water if you're going to be working around power. Get certified by your company to be allowed to open up the panel. If you can change out the fuses, you can probably connect the power probe. If you can't open the panel, then you can install this fixed power adapter. And then you can hook the power probe with the radio up without opening the panel. Look at the wires. Make sure the wires aren't burnt. Stop if there's a burnt wire and get an electrician to come out and repair it. You just need to be careful, and if you don't feel good, don't measure power, because you might if you're feeling not the greatest, maybe you should skip measuring power. But if you feel fine, and you're comfortable with doing it, and you're certified, then you can do it safely and hook it up without any trouble at all. That's what this just kind of says. Don't stand in a puddle of water when you're hooking it up. Need to be trained. Read the manual. And another safety thing, just be safe. And if you're restricted by your company, you can always put the fixed power adapters inside, the permanently installed ones inside your panel. Have an electrician install them, and that way you don't have to you don't have to run the risk of getting harmed if you open the panel if you're not comfortable or your company doesn't want you to. This is just talking about the current, how much you can stand before you get to fatal. I guess this is just wanting to make sure you're safe and practice safe practices when you use it. We talked about this slide. You know, the thermal loading is important. You know, it's been a long time. I bet Ken still sees me hopping around when I found out that motor was ready to burn up. I mean, I was pretty excited when we found one. I mean, it's really neat that you can understand that the motor has too much current flowing through it, and it's going to be thermally loaded and damaged. I like the relationship between the kW and the net torque. I like knowing the input power and the efficiency of the system. All of those are, and we've added the voltage to come up with the line losses. All those are, I think, important to. You know, you can't really save power in your company, minimize your power bill if you don't know where your power losses are. And that's the advantage of the power probe, is to know where your power losses are. This is just showing us to stop the pumping unit with the weights up and the horse's head at the bottom. And we're going to hook our dynamometer up, and we're going to hook the power probe up here in the panel. You disconnect the main power with the switch in the panel, and set the brakes, and then you can hook the equipment up. I made this slide, I don't know how long ago, probably in 1993. So this slide's been around a long time. This is Amrite's panel, and it used to say somewhere in here, put your left hand in your back pocket and touch the panel with your right hand, and that would be your voltage proximity tester. But Ken doesn't like me saying that, so I finally submitted to just go buy a little switch and a little wand and wave it around on the panel and make sure it's not hot. You know, pull this main switch and disconnect the power. Open the box carefully and inspect for any faults. If you have any concerns about safety, stop and have the electrician repair it. This shows inside the panel with the HOA switch. It shows the 3 voltage connectors above the HOA, so we can read the voltage while we're down. And this is the fixed power adapter amp sensors, and this is the clamp-on amp sensors here. This is the one on the left wire. This is the one on the right wire. Notice that the wire goes straight through there, that clamp. If you came over here and put the clamp facing the same way up, if that was going this way, then the wire would be going the wrong way through the clamp. It needs to go facing the transformer that way. And so this one needs to go through facing the transformer. So be cautious, because these wires tend to loop around a little bit, and it's easy to hook it upside down. And then we hook up one upside down, it kills your current. Your current's going to be a flat line, or it's going to be upside down. So it won't blow the thing up. It'll just give you bad data. If you're going to hook up the power probes, hook it up right. You want to get the data. It won't cause any damage. It'll just get you bad data, and you've wasted your time measuring the power. It just shows the 3 current alligator clips hooked on here. Again, I prefer to put these above the HOA switch. I don't like them down here below, because I can't see the voltage. Notice that we want to make sure these jaws are closed, and the wire's going right through the center of the jaw. Both of them go the same way. This is a good picture. It shows right, center, and left. You can see how we've got them connected, right, center, and left. Again, I prefer to have them above the HOA switch, so I can measure the voltage. Now this has it's a metal box. Some boxes are fiberglass or some other kind of material, not magnetic. But here, the this is our transmitter receiver radio for the power probe, and we've got our wiring harness hooked in, and we can communicate with our base station that's far away, and we mount it. We don't really mount it; it just attaches to the panel because it's got a magnet. It just holds onto the panel with the magnet, and that's we want line of sight between the radio and the base station. That's an important part of acquiring data. Now, this slide just saying, you know, if you can't get in the panel, then we have the fixed power adapter. And here's the radio receiver for the power probe screwed right into the panel, and it's saying, hey, you need line of sight to your base. You know, what we recommend is different than this slideshow. This slide shows we want to put the big antenna usually on the sensor and the small antenna on the base station. So you get a better signal if you do that. So I prefer to have the large antenna here and the smaller antenna here, but this was an early on picture that we made. Now this is the kit, not the whole kit, because there's a template that you can use to cut out the hole in the panel. But here's the 3 wires. The black wires go to the different voltages. You know, left, right, and center, the 3-phase voltages. This is your plug that this all comes into. This got some resistors in here that reduce the current and voltage to a really small amount, so it's not dangerous. It's got a waterproofing cap that you can put on here. There's your 2 current transducers to get the amps and voltage, and then we output with the little wireless receiver transmitter, we output the volts, amps, and the kW. Here the electrician is creating, modifying the panel to hook up the fixed power adapter. There's a kit that you can draw and put the holes on, so you can drill it out and hook it up into your panel. This is on the inside looking out. You can see that we've got the connector here attached to the panel, and it's showing that we've reduced the current to a really small milliamp current for the 480 volts is almost nothing. And here's the current sensors and the black wires for the voltages on top of the HOA switch. The current still goes to 0 when you turn it off, so it doesn't really matter where the current sensors are attached. It more matters where the 3 voltage pickups are attached. They need to be on top of the HOA switch. Now here we just have the connector. It's a watertight connector with a cap, and you unscrew the cap and you screw the power transmitter, the receiver transmitter for the power probe, without the harness, right into the side without opening the panel. This works really well, quick and easy, and you avoid opening the panel up. You just push this button to turn it on. It'll indicate it's transmitting by a blinking light. It blinks 1 blink for every tenth of a decimal fraction of how much the battery's charged. 10 blinks would mean the battery's fully charged. And then you can currently simultaneously acquire data with the dynamometer test. Now, we looked at this slide before, and I like this slide because it shows the breakaway and breakover kW, the locked rotor amps, and then it shows this voltage sag when you turn the unit on and represents the line losses. So this slide, to me, I like it. I don't know if anybody else likes it. It's really busy, but that's why I like this slide. Okay, so now we've got everything hooked up right, and we're using our sensor, power probe, and our dynamometer sensor, and we're going to go in and pick a well, and this is showing we're going to pick the V11 well. And we've selected it, and then we go to the lift system, edit lift system, and we make sure we look at the back of the motor and look at the label on the motor and make sure these parameters are correct. The full load amp rating, the RPM rated full load, and then the synchronous speed. And then over here, if we are on pump off controller percentage timer, we're going to input the runtime, and then here's our horsepower rating up here. And if we do a test, we're going to put that information in for that test if we're not 100% run. And it remembers 100% run and uses it in the future, but if you every time you do a test, it's different amount. You put the percent run in right here, or the hours run per day right here under Edit Lift System Prime Mover. We're going to click on dynamometer, start dynamometer test, and then we need to select our sensors, and we can have a dynamometer sensor, a power probe sensor, and a pressure transducer. We could select all those, and so here we're picking our dynamometer sensor, and here we're going to use our power probe. This is from our hardware setup, and we've already got a gas gun selected and a pressure transducer selected. And then this is going to be our power probe, and we can see that the signal is pretty good. Often the signal for the power probe will be the least strong because it's the farthest away. And then we have to have all those selected. The dynamometer sensor is hidden, the pressure transducer is selected, and the power probe selected. And then when we say start acquisition, we'll acquire data from all three sensors. This is just showing us that we've got our three sensors communicating, and we're getting ready to start a test. And we said, okay, we want to adjust the polish rod transducer so it's properly tightened on the polish rod. And once this bar gets in this green area, we can go ahead and click continue. The PRT is properly tightened for a dynamometer test. And this is the Thorman well, the Thorman well, and they usually run that well pretty severely pumped off, so I can usually recognize that dynamometer card. And it's showing that we're acquiring here load and tubing pressure, or pressure with the pressure transducer, acceleration, and volts and amps and kW with the wireless system. Once two strokes are acquired, then we start to see the surface card and pump card in the live mode, and we have this little display here of the power. And so as the well pumps, this little dot goes up and down, representing the instantaneous power being acquired during the stroke. If the well is down for 5 minutes, we're going to take 5 minutes of data plus 3 or 4 minutes after that. If it's down for 10 minutes, or hooking the equipment up, then we would take 10 minutes plus about 3 or 4 or 5 minutes after that. So we want to start acquiring data when the pump unit first turns on to see if the pump is full, and if it's going to pump off, we'd watch it until it pumps off, or maybe we want to see if the pump will pump full, what the pump card looks like when it's full, and what it looks like when it's pumped off. And we're just acquiring data here. We're going to click the stop button to stop acquisition. Now we went to the raw tab, and the raw tab has the different data sensors displayed you can select, and so you can select power and current and voltage, or accelerometer and pressure from the pressure transducer and display down here along with the load. So the raw data lets you see the data versus time. I often will click right here and expand this plot to the full screen because this is kind of scrunched up a little bit, and I like to expand it out. So I usually click right there to increase the display for the full screen. And this just says, acquire the downtime plus 5 minutes more. I think that's a good recommendation. So if you have the well down for 10 minutes hooking this stuff up, and then turn it back on, take data for 10 minutes plus 5 minutes more, that means you'll get the full card, and then you'll get to the conditions you were before you shut the well down. Typically, once you've got enough data, click the stop to stop acquiring data. This is a similar plot that I just showed you guys. That it shows the relationship between power and net torque. They're the same thing. Even though this is units of kW and this is units of inch-pounds of torque, and it's amazing how well they match. This is a relationship it shows this is the analysis plot. It shows the relationship between current flow and voltage. So when the voltage is near 480, then the current's at its minimum. And when the voltage drops, then the current goes up. And that's at the pump unit, and the voltage over at the transformer is probably around 480, 485, and this is a drop due to the current flowing through the line as it's flowing through the well. This is the torque calculations in TAM. We picked a torque tab, and there's also the report that shows the torque. The report's very good on the torque report. There's limited information here. It just shows you the unbalanced and the balanced conditions, and it shows you how far to move the weights and how much the weights weigh that you're going to move. And if you put in the weights that you're going to move, what they weigh, then it tells you how far to move them. If you put in half the weights, it's going to move twice as far because it has to achieve a certain amount of counterbalance, reduction, or increase to balance the units. We click on the power torque calculator. We already talked about that a little bit. This is where you put the weights in. If you haven't put them in already on the edit mode, you can put them in here. And that's how many weights you're going to move to counterbalance. And that's move from the current location. That's move this many weights, pounds of weights, inward from the current location, all those weights, that's 4 weights, in 5.9 inches. My preference is to have all the weights lined up. People sometimes ask that. I don't like to have the unequal counterbalance moment on each side of the gearbox shaft. I think that can cause damage to the gearbox. I've been told that, and then I've been told more recently it doesn't matter, but I tend to still not want to make uneven counterbalance moment on each side of the gearbox shaft. So I tend to keep them equal spacing, top and bottom of the weights on the crank. This is a report, so we click the report button, and you have the option of printing to a printer, sending the report to a PDF file that you can email. If you click email, then it's going to attach the PDF report to the email. I use this quite a bit to increase the size of the display of the information on my screen. I like to click plus about 3 or 4 times sometimes if I want to zoom in and look at a plot on the PDF report. There's a Word report goes to Microsoft Word that you can type in a recommendation summary and insert some graphs. There's a dynamometer graph, the torque report, the power report, and then however you left the analysis plot for this stroke number 8. This is a report for stroke number 8. If you selected the analysis plot to show a certain thing, then that's what will print out when you print this report. You can select an image for your company or your business card. Can be displayed right here. Over this side would be Echometer, and down at the bottom is our contact information. We've already talked about this slide. This is the electrical parameters that you measure. It's nice that it tells you the minimum motor size that you need for the well, and the system efficiency is important. There's also demand charge here, and then there's a demand charge over here. This is the same slide I had at the intro of the other presentation, and I'm a big proponent of measuring motor power and measuring the power during the stroke and using that information to analyze the well. Why are my motors burning up? Why are my efficiencies low? What bearings are bad? Do I have a bad bearing? Why is my power bill too high? All those questions can be answered with this equipment. Ever since I've been around the well analyzer, I've been promoting using the power probe. It's something that's a really valuable tool. So, Gustavo, any more questions left?
No, we don't.
All right. Well, thank you all for attending. Carrie Ann, I guess it's up to you now.
All right. Yep. Thank you, Lynn, for a great presentation. This topic has been requested by several individuals, so it's going to be a great resource to have available. And Gustavo, thank you for hosting the Q&A. We sincerely thank all of you for joining us today for your great questions and comments. In the event you have any follow-up questions, we always welcome your calls and emails, so please do reach out to us. Our next session will be December 2nd on identifying holes in tubing on sucker rod lifted wells. So mark your calendars and we'll get the information out to you in the next couple of weeks. We appreciate your time today. We are so glad you joined us and we look forward to seeing you all again soon. Have a great week. Thank you so much.
Thank you all.
Bye. Thank you.